Hi, I'm Seth, and in this video, I'm going to explain Kendall's coefficient of concordance, also called Kendall's W, which is an index of agreement in rankings. Suppose an executive team is evaluating the extent to which they agree on the organization's current strategic priorities. Thing about priorities is they can't all be number one. They have to exist in some kind of hierarchy or rank orders. That's how you decide what to do in any particular situation. Now, in general, we would expect people with different roles to have different priorities. But when we're thinking about the organization's strategic priorities, theoretically, they should be shared by everyone. So lack of alignment could lead to different units working at cross purposes with one another. And if everyone pushes hard in different directions, you get nowhere. For simplicity, let's say there are 5 executives, as you can see here represented in the rows, and 5 strategic priorities, which you can see in the columns. Let's say independently, they each rank the importance of the priorities from their perspective, and you can see those rankings showing up here. Why would you do something like this? Well, it could be that they just want to get a sense of how aligned they are, or maybe they're about to do some kind of strategic planning meeting or retreat, and they want some measure of whether it works, whether alignment increases following that event. Well, right off the bat, you might notice that no one has the exact same rankings. If you stare at it for a minute, you might get the sense that it seems like people kind of generally agree. For example, I don't see anyone with a ranking of 5, 4, 3, 2, 1. But how close is the agreement in more objective terms? How can we put a number on the level of agreement? For example, if we want to see whether that level of agreement increases or decreases over time, what number would we look to? Well, one way to evaluate agreement in rankings is Kendall's W, sometimes called Kendall's coefficient of concordance. But before I explain that, learn this one weird, cool trick to magically understand all sorts of psychometrics and statistical formulas. Grasping this simple concept is going to unlock a lot of formulas for you. And the trick is fractions. A lot of the transformations and corrections that we use in statistics and psychometrics involve taking some observed statistic and then expressing it as a proportion of the maximum value it could possibly have been. And I'll make a separate video at some point walking through all kinds of examples of this. But for right now, just know that this is a useful trick, and this will be a way to understand Kendall's W in a simple way. Now, a lot of people will show you this abomination when they're teaching you Kendall's W, and you're welcome to puzzle over this formula if you like. I don't find this particularly intuitive. And so I'm not going to walk you through this. Instead, I'm going to represent this formula more clearly. So this is my version of Kendall's W. I think this makes way more sense conceptually. So this SSR bit on top, that represents the extent of agreement. And then we're simply going to divide that by the maximum possible amount of agreement. Okay, it's that same trick that I mentioned a minute ago. How much do they agree out of the maximum that it could be? And that's going to make it so W will range from 0 to 1. Okay, so that will make more sense when I walk you through an example, but let's talk about what these letters mean. So where you see capital R, I'm talking about the sum of a particular column. In other words, the sum of the rankings for a particular target. When I say SS, that stands for sum of squared deviations. That's a measure of how spread out the scores are. Conveniently, the only formula we actually need to know how to calculate, if we're going to do it by hand, is the sum of squared deviations, which you can see right here. So R is the sum of each column, and M subscript R, that's the mean of the R for the different columns. So what we're doing is we're finding the difference between each R and the average R, then we're squaring those and adding them up. That's what this notation says. Okay, so now let's make this make sense by looking at an example. First, let's consider what it would look like if there were perfect disagreement. As you can see, when everybody ranks the targets differently, so here I've set up the rankings for each executive to be as different as possible. When everyone ranks the targets differently, that means the sum of rankings for each target, for each column, comes out to the exact same value. That might seem a little bit tricky, but think it through. Each target is getting a different ranking by each person. For example, in our case, look at priority B. The CEO gave it a 2, the COO gave it a 3, CFO gave it a 4, then a 5, then a 1, right? Because they all gave it a different ranking, the sum of that column has to be, well, in some order or another, 1, 2, 3, 4, and 5, which adds up to 15. And it's going to be the same for every target. Because each rater gave each target a different ranking, the sum has to come out to 1 plus 2 plus 3 plus 4 plus 5 in some order, which is going to equal 15. So here, when we look at the sum of each column, there is 0 variability. It's 15 all the way across. The sum of squares calculation is therefore pretty easy. The average R is 15, so 15 minus 15 is 0. Square that. 15 minus 15 is 0. Square that. Add up a bunch of zeros, and you get 0. Quick sidebar, it's not always going to come out to precisely 0 like this, even if you got perfect disagreement. I set it up with 5 raters and 5 targets, which makes this kind of possible and convenient. But for example, if there were only 4 targets, then you'd have to have some amount of agreement just by chance. So anyway, the point is, with perfect disagreement, the sum of square deviations of the totals for these columns is going to be a small number near 0. Okay, let's flip it around. What if we had perfect agreement? So here you can see theoretically every single person said 1, 2, 3, 4, 5 in that order for their rankings. Now, hopefully it starts to be a little more obvious that the sum for each column has to be different because we only have 1s in this first column. 5 1s adds up to 5. We only have 2s in the second column. 5 2s adds up to 10, and so on. So now these totals are as different as they could possibly be. Remember, with perfect disagreement, the totals had to be all exactly the same. And then you flip it around with perfect agreement, the totals have to be different. Okay, so let's walk through the sum of squared deviations calculation. So the average of 5, 10, 15, 20, 20, 15 is the average of those. So 5 minus 15 is negative 10. We'll square that. 10 minus 15 is negative 5, square that. 15 minus 15 is 0, so on and so forth. Now, if we run this calculation, it's going to come out to 250. What this means is that the level of agreement is going to be somewhere between 0 and 250. That's the range of possible values. Now, for our observed data, we're going to calculate an actual W, and then we're going to divide it by 250, because as you can see, 250 would be the maximum possible. If everyone did agree perfectly, then the result would just be 1, because it'd be 250 divided by 250. So like all proportions, it has to range from 0 to 1, or if you think of it as percentages, 0% to 100%. Let's return to our example to see where we're at. In this particular case, the mean is still 15. Now, if we run through the calculation of saying, okay, 7 minus 15, then square it, 9 minus 15, then if we run through all those calculations to get our index of variability, we're going to get 186, which that seems closer to 250 than it is to 0, but how close? Well, we can divide that W, or that's not a W, that's just the sum of squared deviation. We divide that by the maximum possible, which is 250. That's what gives us the W. And so in this case, 186 divided by 250 is 0.744. So the executives generally agree on the strategic priorities, though it's kind of subjective as to how much agreement is good enough. Is that a good enough level of agreement on a 0 to 1 scale? That's something that the organization has to decide. Now, just to double check that we get the same result as when we use that horrific computational formula from before, here I've plugged in the relevant values into that formula, and it also spits out 0.744. So if you needed to compute it by hand, I guess this would be, this would definitely be a faster way to do it. But I would think of it in terms of the more intuitive formula, the level of agreement out of the maximum possible. Okay, now I'm going to show you how to do this in RStudio. Okay, here we are. I typically, if I'm going to run this, I use the IRR package. So I'm going to load that up real quick. Now I'm going to create a data frame with this data. These are all the same values, the same rankings of these priorities as from the slide presentation. Okay, so one small thing is that when we use this Kendall function for Kendall's W, it's expecting the targets to be in rows, not in columns. So it expects these things to be flipped. That's not how I would think about it, but that's the way it wants it. So I'm going to use the transpose function, which is T. Okay, so I run Kendall, the Kendall function, but instead of throwing this data frame, which I called align, rather than throwing that in, I'm going to throw in the transposed version of it. Let me just show you what the transposed version is. The transposed version is the same thing, but flipped. We've put the rows in columns and the columns in rows. Okay, so let's run this line of code. It does all of that stuff for us very quickly, and you can see it comes out to a W value of 0.744, which is exactly what we calculated before. I'm going to extract from that just that value, 0.744, and I'm going to call it capital W. Here I'm being a little bit bad. People would say if you're going to grab that, you really need to spell out the exact thing you're looking for, which is value. But I like to use the shortest version of it possible. And if I just use V, it'll recognize what I mean. Now, you may notice we've got a p-value down here, but I wouldn't recommend using a chi-square in this particular situation just because we have very small numbers involved. What I would use is a permutation test if you're wanting to do like if you want like a p-value, like null hypothesis significance testing. Okay, so let's do that real quick. I'll show you how to do a quick simulation. So this code right here is going to create 5 rankings. Well, let me just show you. If I run this code, you can see we get, for 5 targets and 5 raters, we just get 5 rankings. Okay, so, and I'm transposing it so that it shows up in the same way we've been thinking about. Don't really worry about that. So here's what we're going to do. I'm going to generate a null distribution empirically using simulations. I'm going to use this code, which comes up. It just sort of randomly assigns rankings for each of the 5 raters. I'm going to make R do that 100,000 times. And for each of those, I'm going to have it run the Kendall analysis and grab the W value, which I've confusingly used V as the subset for that. But anyway, what this is going to do is collect all of those W values into a distribution. And this is going to take a second to do. So I'll go ahead and run it. And then I'm going to create a histogram of all of those values so that we can see what the null distribution looks like. Okay, that took like 30 seconds, but I skipped that for you. Let's just take a look at this histogram. Okay, so here you can see we've got a histogram of W values. These are all from randomly generated data. So you can see a range from 0 to 1. And while if the rankings were just sort of random, you'd expect them to pile up down here in this lower range. It is possible just by random chance to get a W of about 0.7 or 0.744 or even as high as 0.8. It's possible to get it all the way up here, but it's just extremely unlikely. So what a p-value is actually is the proportion in a null distributions that's at least or more extreme than your observed one. So it would say, well, what's the tiny slice over here out of all of this total? So we can actually run that to get an empirically derived p-value, and we get 0.0004999. So about 0.0005. Okay, so that's like a 1 in 2,000 approximately. So it's possible, but not particularly likely that we would see this level of agreement just by chance. And that's really all a significance test gives you, is like the probability that you would see a result at least this extreme if the data were random, or if the true effect were literally 0, which in this case would be as if people were just responding randomly rather than giving actual rankings. Okay, so that does it for R. Let's see, just a few other things I want to mention. If we only had two judges, we could just correlate their ratings. Then it would actually range from -1 to +1 instead of from 0 to 1. With two judges, you could still use W. W and R are algebraically linked. You could think of W as like the generalization of the Spearman correlation to 3 or more judges. Oh, it's also linked to the Friedman test, but I'm not going to go into that right now. Okay, let's think about how could you use this potentially? Here are some other possible applications. Maybe we have an interview, and I'm an IO psychologist, so I keep thinking of all these workplace situations. But let's say we've got an interview panel who's rank ordering a set of finalists for some leadership position. This is how they could evaluate their level of agreement on the rankings. Or maybe there's a process where a committee has to review vendors before selecting one. Maybe they're required to review a certain number of them. Let's suppose that they rank order the vendors. You could use this to figure out how much agreement they have in their rankings. So maybe you have a requirement that there has to be some target level of agreement before you're willing to make a decision. Or maybe you're curious if different managers are evaluating performance of employees similarly. You could have the same managers all rank order the same employees and then evaluate the extent of agreement. And that could be relevant for something like figuring out whether there are fairness issues or whether you need to do some sort of training to get people on the same page about how they're rating people and so on. Okay, here's some other questions that might be interesting to ask when we go back to our strategic alignment scenario. What if we have some sort of intervention for leadership and we want to know, does agreement improve following the intervention? You could use W to evaluate that. Or what if we wanted to evaluate the level of strategic alignment, not just at the leadership level, but for entire departments or for the entire organization? Or maybe we want to compare how top leadership ranks these priorities with how lower level employees rank them to see if leadership and lower level folks are on the same page about what the organization's strategy is. These are issues I might address in future videos based on what people are interested in. Okay, that's it for Kendall's W. If you have questions, thoughts, comments, or concerns, please don't hesitate to reach out. See ya.